Okay, so remember where we left off. We had this least square solutions defined, which was a solution that minimized the norm b minus ax tilde compared to all other b minus ax. Okay, and I just gave you these two, this definition and related theorem that explain what a best approximation is and give you a criterion providing the best approximation as being the projection of the vector v onto the subspace W. Okay, so let's taking these two results, this definition and this result into account, let's go back to our problem of least square solutions. This is something you haven't necessarily seen. Some of you will have seen, some of us won't have seen. I will give a few examples in the worksheets that you will have for tutorials. I will give a few examples and maybe ask TAs to go over this. This is not complicated. It's not really what the course is about, but it's interesting to know. And so we're going to use it as I explain how it works, okay? So if you think of any vector in Rn, the vector Ax, because A is a matrix and multiplied by x, I get a vector, okay? Ax is a vector and we say it belongs to the column space of the matrix A. And this is simple. So you have a matrix A. The column space is the space spanned by the vectors that correspond to the columns of A. The same way we call row space of a matrix A the space spanned by the rows of A. Okay, I won't get into too much detail about this. I'll just point out, for instance, suppose I have a square matrix and that it's invertible, then the row space and the column space and the row space actually, but both are going to span the entire space. Okay, so they're going to span Rn. But here, remember that the matrix we are looking at, for instance, here has 2 columns and n rows. So this is quite different from a situation of having a square matrix. That matrix is definitely not square. And the column space here is simply the space spanned by these 2 vectors. Okay? Now, okay, so let's go back to this. So for any vector x, Ax is in the column space of A. Okay? Now, since x is in Rn, Ax is in a column space of A, okay, which we denote col of A. This means that a least square solution of Ax equals b, that's a vector y tilde that's in the column space of A, okay? And that is a least square solution. That means that for any other vector y in the column space of A, because remember, y is equal to Ax essentially. So for any other vector y in the column space of A, I'm going to have that the norm of b minus y tilde is less than or equal to the norm of b minus y. And if you flash back to a slide ago, this looks remarkably like what we wrote on this slide, okay? And so I'm going to show you how you would put these two things together, okay? So the first thing I just stated is that the least square solution of Ax equals b is going to be a vector y tilde in the column space of A, such that this inequality is preserved. Okay, so this is what I just stated. And I've reformulated the best approximation theorem to include the definition of the best approximation. Okay, so we can think of this refreshed theorem as containing both the definition of the best approximation and the theorem. Okay, so in view of this, that best approximation theorem would read this way. For a vector space V with an inner product and a subspace W in that vector space, and a vector V in V, then the projection onto W of the vector V, and that's, of course, the projection on W is an element in W, okay? That's the best approximation to V in W, which means that for any W in the subspace W that is not the projection, the norm of V minus the projection is less than the norm of V minus W. So when you look at this first statement, which is the one I obtained on the previous page, and this theorem, you can see that they're saying exactly the same thing, provided you match the terms, okay? So I said the least square solution of AX equals B is a vector space, y tilde in column space of A, such that this is true. So all I need to do is what I've done here. I need to identify the terms in this theorem to the terms in this statement. So if I want to match these two things, what do I have to say? I have to say that W in the theorem is, actually I'm referring to the column space of A. That the vector V in the theorem is the vector B here. You see, here I have V minus projection. Here I have B minus y tilde. And, well, the last one that's missing, well, there's a W and a Y, but that doesn't matter, okay? We can suppose that they're, let's call W, let's agree to call WY or whichever way you want, okay? But the last one that's remaining here in this term is this term. So that means V is B, as I said, but y tilde is then the projection, and now it's on W, but I've said that W is column space of A. So this is the projection on column space of A of, and that was B, but I've said this is V. So y tilde is the projection on the column space of A of the vector B. Okay, so that means that theorem tells me that y tilde equals to the projection on the column space of A of the vector B is that solution that I'm looking for. Okay, so if x tilde is a least squares solution of AX equals B, then y tilde equals to A times x tilde is equal to the projection on the column space of A of a vector B. Okay? And we can use this to go even a little further. Okay? So we have, if we look at this vector here, okay, B is a vector, AX tilde is a vector. So B minus AX tilde is a vector. And B minus AX tilde is the same thing as B minus the projection on the column space of A of B. And that's the vector perpendicular projection on the column space of A of B. So I will add an exercise to show you this, okay? This is something I haven't defined, but it's the orthogonal projection onto the column space of A, okay? But I'll add a little exercise so that you can see what this is about. Now, it's easy to show, and that will be an exercise, that this vector here is orthogonal. Okay, this sign here means orthogonal to the column space of A. Okay, and it's not at all complicated to show. So what that means when we've written this here is that all the columns in A, so when we say this vector is orthogonal to the column space of A, what this means is that all the columns in A, I'm going to call them bold A sub I, so that's column I in A. Orthogonality, we have seen in the refresher on first year that two vectors are orthogonal if their dot product is 0. And this is what we write here. AI, so a column I in A, must be orthogonal to this here, which ends up being this, okay? So AI is orthogonal to B minus AX tilde. That means their dot product is 0. And this 0 here, actually, yes, this 0 here is a scalar 0, okay? This is a vector, and this is another vector. So the result of the dot product of two vectors is a vector. Sorry, it's a scalar. And so this is a number. This is 0, the number. And when we write this, I think I mentioned, yes, I remember I mentioned it in the review, writing that the vector u and v, the dot product of u and v is the same thing as the product of u transpose and v. And this is what we're doing here. AI dot b minus ax tilde is nothing but, I mean, it's equivalent as AI transpose. So this is a row vector that I'm multiplying by a column vector, and the elements multiply one by one until and sum, and the number you get at the end is the dot product. So you can either take the dot of two vectors, or you can multiply on the left by the transpose of a vector. So this means that for all columns of A, we have this relationship. AI transpose times B minus AX tilde is equal to 0. And that's true, as I just pointed out, for all columns of A. So I take a column of A, I flip it sideways, I put it on the on its side, and I multiply it on the right by B minus AX tilde, and I get 0. But I can do that for every column of A that I take, I can put on its side, multiply on the right by the vector B minus AX tilde, and get 0. That means I can take the first column and do it, second column and do it, third column and do it, etc. And what does it mean to be taking each column and putting it on its side? Well, that's the same thing as transposing the matrix A. So when I write that this is true for all I, this is equivalent to saying that A transpose, this time the matrix A, times the vector B minus AX tilde is equal to, and now this is a vector because I have all the columns of A are giving me the same result, so I have a vector of zeros there on the right. Okay? And that means that I can now perform some matrix arithmetic. So if I write this equation here, you see, well, this is A transpose times the difference between two vectors. And we know that matrix multiplication is distributive over vector addition or subtraction. So I can expand this. This is A transpose B minus A transpose A X tilde. And this is what I've written here. Okay, I've simply expanded this this product, this subtraction. Okay, now when I write this, I can also move this term here that has a minus sign to the other side of the equal sign. So this means that I get A transpose B is equal to A transpose A X tilde. Let's write it the other way. Okay, I'm just, that last line is I'm just flipping the left and the right hand side of the equal sign. So A transpose AX tilde is equal to A transpose B. And that is a linear system. Okay. And it's what we call the normal equations for X tilde. Okay. This discussion, and again, in this course, we're not going to do formal proofs, but I wanted to show you where the next theorem is coming from, because otherwise it sort of doesn't make a lot of sense to have the matrices that you see in there. And so that's where those transposes are coming from in the next theorem, which I'll show you right now. So this is called the least squares theorem. So take a matrix in Mn. Oops, I have a typo here. This should be a lowercase m, not an uppercase m. Oops, what am I doing? Yes. So let A be a matrix in Mn and B a vector in Rm. Then the least square problem, Ax equals B, always has at least one least square solution X tilde. You're not guaranteed uniqueness of that solution, but you know that you're always going to have at least one. Okay. Then we have the following equivalence. X tilde is a least square solution to Ax equals B, if and only if X tilde is a solution to the normal equations A transpose A times X tilde is equal to A transpose B. Okay. And the last case is, when does it happen that you actually do have uniqueness of the least square solution? Well, that happens in the following case. So if A has linearly independent columns, this is equivalent to saying that A transpose A is invertible. And just a word before I go any further, I'll remind you that I showed you during the review of linear algebra, of first year linear algebra at the beginning of classes, that if you have any non-square matrix, then A transpose A and A transpose are square matrices, okay? So when we're talking about A transpose A being invertible, it doesn't matter that A is itself in Mn. A transpose A is a square matrix. Okay, so if you need, go back to this this discussion we had at that point. I'll remind you also that the matrix we get is also symmetric. That was something else that we proved about this. So let's assume that A has linearly independent columns, and as I pointed out, this is equivalent to A transpose A being invertible. Then if this is the case, so if A transpose A is invertible, then the least square solution is unique and is given by X tilde equals A transpose times A inverse A transpose times B. And that is simply obtained from the normal equations. Okay, so if I want to, you can see it right here. So if that matrix here on the left of X tilde is invertible, I can multiply to the left on both sides of this equation by A transpose A inverse. When I do so, I get this, so multiplying on the left by A transpose A inverse the matrix A transpose A, that just gives identity. So on the left we get X tilde only remaining, and on the right we get this term here, okay? So this is simply solving a linear system when you have an invertible matrix, which it is because of the assumption here. As I said, we will not show 3. It is not hard. I just did so. Okay. Essentially, I mean, I did not show you the part that says that this equivalence is true. Okay, but once you have the equivalence, it's very, very easy to see how to construct the solution. And that is going to help us construct a solution to our problem. And what I will do in the next video is I will handwrite the solution corresponding to the problem we were looking at in the previous video. And we will see that this solution that I picked a bit random, not randomly, but that I sort of guesstimated, and which turns out to be the right solution, we will see that this is the right solution. Okay. Okay, I want to take a little time to show you how to do the computation for one particular linear least squares problem, which is the one that we had been looking at a little bit since the beginning. So I remind you that we have 3 points that are 1, 3, 2, 5, and 3, 4. Okay. What we want to do is we want to solve the least squares problem, AX equals B, where the matrix A is obtained by solving the linear affine problem at the different points. Okay, and B is the right-hand side of this, and X are the unknowns. So let's do this. Of course, you would go much faster in the future, but so the curve we want to fit is here the line y equals a plus bx. Okay, so at 1, 3, we get what, when we replace y by the value 1, with the value in the point 1, 3, which is 3, 3 equals a plus b times x, which is 1. At 2, 5, what we get is that 5 is equal to a plus 2b. And finally, at 3, 4, we get that 4 is equal to a plus 3b, which means that the matrix A is the matrix of the coefficients of A and B. So that's 1, 1 for the first row, 1, 2 for the second row, and 1, 3 for the third row. Okay. B is the right hand side. Well, we're here, it turns out to be the left, but okay, so this is 3, 5, and 4. And finally, X is just AB. Okay. Now, we have seen that to solve this problem, we have to look at the matrix A transpose A. Okay, so A transpose is equal to, this is just the matrix above where I'm flipping rows and columns. So this is the matrix 1, 1, 1, and 1, 2, 3. I'm not going to do the details of the computation. This is, of course, something you have to be able to do very quickly by hand. But let me go directly. So what we find that A transpose A is equal to, so I've done the computation offline, 3, 6, 6, 14. Okay, and remember that for any matrix A, non-square, A transpose are symmetric. And so this is a sort of check that you can perform. Is this matrix here symmetric? Yes, it is indeed, because the diagonal terms equal something. We don't really care, but the off-diagonal terms match across the diagonal. Okay? So I'll remind you that the theorem we saw said that if this matrix is this matrix is going to be invertible if the linear remember, so ATA invertible if and only if A has linearly independent columns. Okay, well, here we can just check and see that A transpose A is indeed invertible. I mean, that determinant is 3 times 14, which is 42 minus 36, so the determinant is 6. We're good. But just so that it's clear, of course, if you have a bigger matrix, it might be harder to say, whereas finding that in this matrix here, the columns are linearly independent is quite simple. Okay, if you look at the first column, if you look at the two columns, let's put it that way. If you look at the two columns, these two columns would be linearly dependent if one was a multiple of the other. And so it's clear that if I wanted to replicate the first entry in the first column, I would have to multiply by 1 to get the second column. But if I want to get the second entry, I multiply by 2 and the third entry by 3. So clearly there is not a value C such that C times the first column is equal to the second column. So we have linear independence. Okay. So we know from both ways that the the matrix A transpose A is invertible. And so what does that mean? Well, if you recall, what we saw is that we had the normal equations, normal system, which took the form A transpose A X equals A transpose B. Now, because A transpose A is invertible, A transpose A inverse exists. Okay, well, because, but it's actually an equivalence. Okay, so that means I can multiply both sides of the normal equation by A transpose A inverse. So I get A transpose A inverse times, let me just put a parenthesis here just to really emphasize what we're doing. A transpose A, inverse A transpose B. And so of course here I'm multiplying a matrix by its inverse. So what I get is identity. So this is X, okay, because I'm multiplying on the left by identity, and X equals to A transpose A inverse A transpose B. Okay, so let's continue. So we saw what A transpose A was. Now I won't get into the detail. This is also something you have to know how to do. A transpose A inverse, especially this is a 2 by 2 matrix, so you shouldn't have to do the computations. So this matrix takes the form 7/3 minus 1 minus 1 and a half. And now to go further, I need to multiply here by A transpose. So let's do this now. So A transpose A inverse times A transpose, what we get now is a matrix that takes the form 4/3, 1/3, minus 2/3, minus a half, 0 and a half. And so finally, we have that x tilde, okay, our solution, our least square solution, which we know to be unique this time. X tilde is A transpose A inverse A transpose B, and that equals to, and I'll let you do the computation if you want to check, 3 1/2, which, if you recall, is the solution I came up with like this. I did not know that this would actually work out this well. So this means that y equals to 3 plus, 3 plus 1/2 of x is the least squares solution. And as I said, here it is unique. Okay, so you see how this works. And so it's not always going to be possible to solve. And in that case, you're going to do elementary row operations on matrices. I will come up with another example to show you this. Okay, next question. Suppose that instead of trying to fit an affine function, we wanted to fit something a bit more evolved. So for instance, suppose we want to do a quadratic function like this, or perhaps even some exponential function, okay? Here I'm looking for A0, A1, and A2. Here I would be looking for a K0 and a K1. So how does that change, and how would we proceed? So I'm going to start with the case of a quadratic to explain, and I'll point out that this method would be valid for any type of polynomial function, okay? So whether it's a quadratic, a higher order polynomial, the reasoning would be the same. I'm going to limit myself to the quadratic, but you'll see how things work exactly the same way for other types of polynomials. So the problem is the same as before. We have data points x1, y1, x2, y2, and so on and so forth until xn, yn. And we want to fit this quadratic function y equals a0 plus a1x plus a2x squared. So we proceed exactly like we had done before. At the point x1, y1, the approximation that I get by using the function y equals a0 plus a1x plus a2x squared is y1 tilde, this new value of y, that equals a0 plus a1x1 plus a2x1 squared. And we can continue this all the way to xn, yn, at which point we have yn tilde equals to a0 plus a1xn plus a2xn squared. Okay, so nothing changes from the previous case, except that we've added these terms here. So in terms of the error, what do we get? So epsilon 1 is then exactly the same way as we did before, y1 minus y1 tilde. Epsilon n is yn minus yn tilde. In this case, y1 tilde is this function, this value that we just computed, and all the way down to yn tilde, which is this value that we just computed. And exactly as we had done for the affine function a plus bx, well, we can write this in matrix form, or matrix and vector form, in the form of E equals b minus ax, where E is the error function epsilon 1 to epsilon n. X is the unknown, so the values of A0, A1, and A2 that are giving us the best fit. B is the right-hand side, so the known abscissas of the data points. And finally, the matrix A is very similar to the one before, except it has one more column. So if you go back to what we did for the affine function, we had two columns, the column 1, the column x1 to xn. Here we're adding a column with x1 squared all the way to xn squared. This is exactly the same thing, except that I am now squaring in this matrix the x values at the data points. This is exactly of the same form as we had before. So our theorem 6 that we saw before, so this theorem here, that the least squares theorem, does apply exactly the same way as it had before. We have A here, which is in M of n3, okay? There's n data points, and B is in Rn. And that's it. And I'm now going to show you an example. Well, I mean, I'm going to take the same example as we had before, but to change things a little bit compared to what we did before, I'm going to this time treat the problem using software instead of using instead of writing down the solution. Okay. Okay, I want to continue working the example we were working on last time, but this time I want to fit a quadratic, and I also want to show you how to do it in R rather than by hand as we had done last time. So I remind you that the points we were looking at are these 3 points, 1, 3, 2, 5, and 3, 4, and that they look something like this. So first of all, when you think about a problem like this, this looks like a good candidate for fitting a quadratic through these 3 points. Because if you think about it, if I draw an upside down, I mean a quadratic facing down, I can probably get something fitting through these things quite well. And so let's take a look at this. So I remind you that the problem is the following way. So we want to fit this a0 plus a1x plus a2x squared, and we are going to use the matrix A and the vector B. So the matrix A is the matrix where the columns are the coefficients in front of the a0, a1, and a2 when evaluated at x, xi, the data points. So the first column is just once because x takes the power 0 in this equation. We could very much write it the following way. We could write it that way because x to the power 0 is 1. Okay, so that means all those coefficients are just 1 here. The second column is the column with the values x1 to xn. So these are the coefficients in front of a1 here. And finally, the third column are the coefficients in front of a2, which are the x squared. So our matrix A is going to have 3 columns, and because there are 3 data points, 3 lines, 3 rows. B is the vector that contains the y values of the data points. So let's make those two. So A, I am going to write, is a matrix. And so if you recall last time, I pointed out that when you're entering a matrix in R, typically by default, it does so column by column. And here, column by column makes more sense than row by row, because I know very well what those columns are. So I'm going to do it column by column. So I'm providing a vector, and then I'm not going to use the keyword by row equals true. I'm going to just leave it like this, and so it will make columns. So my first column is 1, 1, 1. My second column is x1 to xn. So the first value of x is 1, the second value of x is 2, and the third value of x is 3. The third column is x1 to xn squared. So the first is 1 squared, 2 squared, 3 squared. And this matrix, you need to indicate this, has 3 rows, number of rows equals 3, and number of columns equals 3. The vector B is just a column vector that has entries, the y values. So the y values are 3, 5, and 4. And just to check and show that it's okay, I'm just going to get them printed out. So A is the matrix as we had expected, 1, 1, 1, 1, 2, 3, 1, 4, 9. B is the matrix 3, 5, 4, column vector 3, 5, 4. So first observation, if you go back to the least squares theorem, we know that the matrix A transpose A is going to be invertible if and only if the columns of the matrix A are linearly independent. And here you can see clearly that such is the case, because there's no C that I can multiply this vector of 1s by to get this vector or this vector. And likewise, there's no C that I can multiply this guy by, the middle one, to get either of those, and etc. Okay, and let's just check this. Okay, so I'm going to take A transpose A. Transpose in R is obtained by going T of A. Okay, and I remind you that, so if I just do T of A, I get the matrix A transposed. 1, 1, 1 is the first row, 1, 2, 3 is the second row, 1, 4, 9 is the third row. Now, I remind you also that matrix products in R, proper matrix products, not entry by entry matrix products, are obtained by going percent times percent. So if I compute transpose of A times A, so first of all, remember, transpose of A times A is always symmetric. Is that going to work? Yes, I get a symmetric matrix. You can see that the off-diagonal entries, 6 and 6, 14 and 14, 36 and 36 match. Okay. Second point, that matrix should be invertible. So its determinant should be non-zero. It is probably equal to 4. I'm not quite sure. Is this numerical imprecision or not, but you get a value close to 4. Perhaps it's 4. I mean, we could check it by hand, but it's not really worth it. What is clear is that this determinant is non-zero, so we're good for this. And so I remind you that then the solution to the linear least square problem is given by A transpose times A inverse times A transpose. Let me write it down. So let me switch to, oops, not, I need to switch this to a writing thing. So the solution is A transpose A inverse times A transpose times B. Okay, so that's what I'm looking for. So let's compute this value now. So I remind you that what I pointed out last time, if I want to invert a matrix in R, I have to use the function solve, but without a second argument. So what I want to solve is transpose A times A. Okay, so that's the A transpose A here. So if I do this, I get this matrix. I need to multiply this by the transpose of A again. And then I need to multiply, multiply this again by B. And I'm going to store this in, let's call it solution. Okay, so what does solution look like? Okay, it's a vector, of course. It's a vector with 3 rows. So this is the coefficient A0, A1, and A2. So how did we do? Well, we want to plot again, so maybe I don't need to copy this because I've already got the points in memory, but I will take this plot again. Let's plot this. Okay. Now, what I need to do in the previous example, when I was fitting a affine function, I could use the function AB line because it creates a straight line. Here, this is a bit more complicated because it's not a straight line. There is no straightforward function to do this. We could create, well, actually, why not? Let's make a function. Let's say that f is the quadratic. Let's call it fq for quadratic. And let's, because functions are really useful, so I'm going to emphasize the use of it. So the function is going to be a function of x and of the solution. And what is it going to do? It's going to return the value of solution of 1 is A0. So this is sol of 1, oops, plus sol of 2, this is A1 times x, plus sol of 3 times x squared. So if I provide a value or values plural of x to this function, I'm going to get f of x equals to the quadratic. What values of x do I want? Well, let me see, I want to plot from, let's say, about here to see what the curve looks like. So I'm going to create a sequence of values of x, which I simply do by using the function sequence. So from 0.5 to 3.5 by steps of, let's say, 0.01. If I do this, let me just go below. You can see x has been created as this vector from 0.5 to 3.5 by steps of 0, 1. So, okay. Now, what do I want to do? Well, I have these values of x. So one remark is that in R, the first call to plot defines the plot window and etc. So when I call plot like this, this is produced. The limits for the axes are chosen, the axes labels are written, and so on. Any subsequent plot that I make to the same plot has to use a different function. So I can't use plot again. And what I have here is a line. So what I'm going to use is lines. And let's just say, well, I need to plot x and fq of x. Oh, I forgot solution as an argument. Okay, fq of x and solution, because it doesn't know what solution is. Okay, let's evaluate this. Oh, this is looking quite good. Okay, so you can see that the curve is going quite nicely through these 3 points. I've only got 3 points, so it's quite easy to drive a quadratic through 3 points like this. Okay, but this is looking quite good. Actually, let's see how good we did. So instead of saying that x is all these values, let's just say that x is the values from 1 to 3, which are our actual data points. Okay, so then if I compute fq of x and solution, I get, well, that for values, so these might be numerical imprecisions. I mean, we'd have to check precisely. They might be numerical imprecisions. They might just be that it's not quite the value. But if you remember, what we should have is 1, 3. This point is 1, 3. This point is 2, 5. And this point is 3, 4. We're very close. Even if we assume that this is not the real solution, it is something that is very close to what we're using. And that's it for this.